This dark oxygen discovery in the deep sea changes everything we know about deep sea mining. We're going to talk about it on today's episode of the How to Protect the Ocean podcast. Let's start the show. Hey everybody, welcome back to another exciting episode of the How to Protect the Ocean podcast. I am your host, Andrew Lewin. This is the podcast where you find out what's happening with the ocean, how you can speak up for the ocean, and what you can do to live for a better ocean by taking action. And for a long time, for probably the last 10 years, deep sea mining has been one of the issues that people and scientists and all sorts of people have been worried about for a long time. There's been a moratorium on deep sea mining until recently, when certain countries have decided, even though a lot of other countries said we're going to keep the moratorium in place, they're going to start exploring whether deep sea mining is going to be efficient, is going to make money. The reason why we're doing deep sea mining is for specific metals like cobalt that will go into electric vehicle batteries, EV batteries, so that we can do better for the planet. But are we going to do better for the planet, right? Do we actually have to mess up the deep sea by mining the metals in the deep sea to make the planet better, because we will be able to create more cars that have less, fossil fuel exhaust and greenhouse gases going into the atmosphere? We're going to mess up the ocean, which provides us with the oxygen we need to breathe, and the deep sea, which we know virtually nothing about when you really think about it, and we're going to deep sea mine it to make the planet better. It just doesn't really add up for a lot of people. Although, the people who are doing the work and trying to build more EVs are saying they're doing it better, like they're doing a good thing for the planet. Are they really? Is this really what needs to be done? Can we not come up with something different? And that's been the debate. That's really been the debate. Is this really the thing that we need to do to make the planet better? Can we not find an alternative? And even if we did, I remember talking to Dr. Andrew Thaler, who is a deep sea biologist, and he's done a lot of work with deep sea mining, including authoring and being the chief editor of a deep sea mining magazine for quite some time. He even said that even though if we start deep sea mining today, the metals that will be mined from the deep sea won't be put into production until about 50 years down the road. Will we still need those metals in our batteries, in our EV batteries down at that point in time? The battery technology is getting better and better, and we're requiring less and less of these metals. Now, the problem with mining these metals right now is they're mined in, cobalt mines in Africa, which do not have good human rights history in terms of the mining. There are rumors and videos showing children mining. It looks chaotic. It doesn't look like they're being taken care of like we have in some mines in North America and in the West, as well as in Europe. So, obviously a lot of problems with that. However, when we start to look at the deep sea, and we're doing more and more studies on the deep sea, a new discovery was made, and that some of those nodules that are going to be mined are actually good for the deep sea and probably belong in the deep sea. Why? Was it because they create oxygen? That's right. The deep sea, which is a dark zone, it's not a photozone, meaning light from the sun does not penetrate down to the 2,000 meters or 6,000 meters or even past 100 meters, let's say, to get to light up the area. And why is that important? Why do we think that when there's no light, we don't get oxygen? Because normally we think, hey, photosynthesis gives us oxygen. The process of plants taking in carbon dioxide and spitting out oxygen through that process is what really gives us the oxygen that we need to breathe. So we look at plants, we look at trees, we look at phytoplankton from the ocean. That produces a lot of oxygen. That's why we say every second breath you take, you should thank the ocean and the phytoplankton in the ocean that produces the oxygen that provides us with that oxygen to breathe, with the great air that we breathe in now. But now, that light doesn't penetrate down into the deep sea, yet these nodules that are on the bottom are actually areas where there's high oxygen levels. So the researchers that published this study in a scientific journal called Nature Geoscience, they were quite surprised, because as they had their detectors, as they had their instruments to detect oxygen down towards the bottom of the sea, they noticed that oxygen was increasing when normally it decreases. So why does this increase? They don't know. They thought there was something wrong with the sensors. So they sent down different sensors, right? Better sensors. And they noticed that they were having the same results. Higher oxygen, increased oxygen as they got towards the bottom. They're like, what is the difference now where we're seeing, hey, there's an increased oxygen in these certain areas? And what they noticed was that there were these nodules that are known for deep sea mining, that are sought after for deep sea mining. These are nodules that are made up of cobalt, manganese, and nickel. And if they're all jumbled up together, they make this like polymetallic matrix. And it's like this mix of like basically metals, right? And when these are mixed, and then a single polymetallic nodule will produce about 0.95 volts. Now, hold on a second with me. Just stay with me for a little bit, because I'm going to tell you why this is important. When they're clustered together, right? Not the singular one that has 0.95 volts, but when they're clustered together, they can actually reach a voltage of 1.5 volts. Why is that important? Because that's what it takes to split oxygen from water. So in the deep sea, there's a lot of water, right? It's pressurized, and it takes about 1.5 volts to split the oxygen from the water, the H2O molecule, and so you will get oxygen. So when you have those nodules there, it produces enough voltage to have that reaction happen without light there. The light produces the voltage to have that reaction to happen. However, when you're in the deep sea, you don't have light, so you have these nodules. So in areas where these nodules are, you get a little bit more biodiverse animals. You still get a diversity of animals there. When there are no nodules on the seafloor, you're not getting as many animals out there. You're not getting the diversity. You're not getting that complexity. So these nodules, which are sought after for deep sea mining, are also good for oxygen. So this begs the question, what do we do? From a conservation perspective, from an ocean perspective, how does this change the sort of sought after deep sea mining that countries are looking for? How does this change the companies who have spent millions upon millions upon millions, maybe tens of, even hundreds of millions, trying to find ways to efficiently extract these nodules from the deep sea without harming, the surrounding deep sea areas? What do we say to these companies? Is this the thing that will ban deep sea mining, knowing that having oxygen down there is going to be really important for these habitats, right? Really important for the geochemical processes in the ocean, in the deep sea ocean. If we take those out, what is that going to do to the deep sea? We're just scratching the surface with its discovery, but this is a massive discovery in deep sea science. This is something that could change everything. This 1.5 volts basically appears to, like the authors say, they discovered a natural geobattery. That was from Franz Geiger from the University of Northwestern University. He's a chemist. Says these geobatteries are the basis for a possible explanation of the Earth's dark oxygen production. So knowing that oxygen is produced in the deep sea is one discovery. Knowing how it's produced is another. Obviously, there are more experiments that need to be done, more studies that need to be researched, and we need to find out how this is going to happen. But this is huge, and he says, this is a reason why such dead zones persist for decades until unknown. So they did actually do, in 2016, 2017, marine biologists visited sites that were mined in the 1980s. So deep sea sites that were mined in the 1980s, and found that not even bacteria had recovered in mined areas. In unmined regions, however, marine life flourished. So why such dead zones persist for decades is still unknown. But however, this puts a major asterisk onto strategies for seafloor mining, as ocean floor fauna diversity in nodule-rich areas is higher than the most diverse tropical rainforests. That is insane, right? This is why we need to do more discovery. We need to be doing more exploration in the deep sea. We need to find out why this is happening, where this is persisting, and how that it affects the deep sea. Right? How do we look at what we do? And it's really interesting because it says ancient microbial cyanobacteria have long been credited for first supplying oxygen the oxygen required for the evolution of complex life billions of years ago as a waste product from photosynthesis, turning sunlight into their energy source. We now know that there's oxygen produced in the deep sea where there's no light whatsoever, right? That is huge. That is massive. So we have to revisit the question of, where could aerobic life have begun? We don't know. That's another question that could be answered. There's more information in the Nature Geoscience publication. I'll link to it in the show notes. But this is a huge discovery. This is massive. This could change the way we see deep sea mining. This could answer that question. Should we be mining the deep sea, especially for nodules, taking those nodules out of habitats where it produces oxygen? And what is that going to do to the deep sea? How is that going to affect the processes that work? How are those animals that are not there, if there's mining that happens, what is that going to do to the deep sea if those animals are absent in those particular areas? How's that going to affect? We all know the deep sea is connected. We all know the ocean is connected in a variety of ways. We know that some crabs, some fish, all these different organisms, the way they even disperse their larvae, right? Or even their eggs before they're even fertilized. Sometimes those eggs will travel, a couple of feet. Other times it'll travel a number of kilometers just to, disperse as much as possible. And so we know the ocean is connected in certain spots, and certain organisms will fill and become like a source for other places in terms of the way they disperse their young. And so how is that going to be affected in the deep sea? Is that going to be affected, or are there similar processes for animals in the deep sea that help, populate other areas of the deep sea? We're going to find that out soon enough, I'm sure. But should we be deep sea mining knowing this information about dark oxygen? That's what we're going to find out soon enough. I'd love to hear your thoughts, though. I'm going to put a poll in our Spotify account, because you can do that. I can actually add a poll. I would love for you to answer that. Go over to Spotify, listen to this, and just answer the poll. Do you think this will affect the way we do deep sea mining, or if we're going to do deep sea mining at all? Love to hear from you. And this is also going to be on YouTube, so if you want to put a comment down below, feel free to do so and answer that question. I'd love to hear your thoughts on this, because this is the beginning of a conversation. I want to hear your thoughts on this as much as possible. And you can also DM me on Instagram at How to Protect the Ocean. So many ways to get a hold of me, but that's why we do this podcast. Anyway, thank you so much for joining me on today's episode of the How to Protect the Ocean podcast. I'm your host, Andrew Lewin. Have a great day. We'll talk to you next time, and happy conservation.